When space exploration first became a real possibility, people wanted to get as much stuff into low Earth orbit as possible. This led to a lot of unconventional rockets being designed, and that's what we're going to be talking about today. Starting off with Wernher von Braun. He had a plethora of interesting concepts. If you don't know about him, he was a part-time German extremist, full-time space nerd. He helped pioneer liquid-fueled rockets, which may have been used to bomb Britain, but that's not the point right now. You see, after the war, he wrote a book called Project Mars, a technical tale, which described how future humans would go to Mars. He envisioned a fleet of 10 ships constructed in low Earth orbit by reusable spaceplanes. We'll talk about those later. The ships he envisioned were massive and would house 50 crew. 3 of the ships would have the crew compartments replaced with large winged landers, which would descend through Mars's thick atmosphere and explore a land of rivers and lush vegetation. Well, he may have got some things wrong about Mars, but the rocket designs he made were actually quite solid. For 1948. Wernher von Braun also had his sights set on the moon. Since the moon has no atmosphere, there's no need for a separate aerodynamic lander. So you could just slap some landing legs on there, and now you got a lunar-capable craft. To give you a sense of scale, here's it compared to Starship. I'll even throw in the lem to show you how big this thing is. Now you're probably wondering how they plan to build such a big thing in orbit. Well, Wernher von Braun designed a heavy lift, reusable launch vehicle known as the ferry rocket. Remember from 20 seconds ago? Its design was very short and fat compared to modern rockets. This allowed it to hold bigger fuel tanks, which it sure needed since the engines designed only would have an ISP of 270. I guess hexagons aren't the most efficient engine design after all. This rocket needed 3 stages in order to get into orbit, while modern rockets only really need 2. Again, this is probably because of the crappy engines. The 3rd stage would make it into orbit and carry the cargo, which would probably be parts for the aforementioned spacecraft or a cool rotating space station. Once all the orbital shenanigans were done, it would re-enter the atmosphere and glide down on the runway like a space shuttle. Hey you, ever wanted to launch an entire space station in a single rocket? Well, say hello to the Sea Dragon. This behemoth was so big that it had to be launched from the ocean, since it would destroy any launch pad on land. It had 2 stages, and unlike most rockets, the upper stage was actually slightly bigger than the lower stage. This is because the lower stage was designed to be as big and simple as possible. During liftoff, the main engine, along with 4 radial engines, would ignite. The upper stage was actually a bit more complex, featuring an expanding nozzle that wrapped around the lower stage and unfurled after stage separation. Believe it or not, this rocket was actually partially reusable. After stage separation, the lower stage would deploy a drag ring to slow it down just enough to prevent it from destroying itself on landing. Now let's talk results. How much payload could this thing carry? Just about 1.2 million pounds. For comparison, the ISS weighs 925,000 pounds, which took over 40 launches to construct. Again, this rocket wasn't really that unconventional as it just was big. But this next rocket I'm going to talk about was a pioneer for nuclear rocketry. Oh, you must be talking about the safe and efficient Project Nerva. Of course, I'm talking about Project Orion. This rocket would propel itself by ejecting thousands of small nuclear bombs, then bouncing off the explosion over and over again. This pusher plate was designed to be very, very strong so that it could be able to withstand days of constant bombardment, meaning constant acceleration. Something like this would be able to reach Mars in just a few weeks, or even be capable of interstellar travel. But because you can't really detonate a nuke on a launch pad, the entire thing was mounted on the Saturn V first stage. This would still require detonating hundreds of nuclear bombs within Earth's atmosphere. And this project was eventually scrapped due to environmental concerns, among other reasons. At this point in time, all liquid-fueled rockets were bipropellant engines. One of the most efficient combinations of this was liquid oxygen and liquid hydrogen. It's clean burning and really powerful, but oxygen isn't the best oxidizer on the periodic table. That title goes to fluorine. Now you could react fluorine with hydrogen, but there's a better way to do it. Instead of hydrogen being the fuel, you could have lithium. It's more dense than hydrogen, and the oxidation of lithium has one of the highest energy per kilogram of any chemical reaction. So this is how the engine would work. First, fluorine would be injected, then a wee bit of liquid hydrogen was added to react with the fluorine and warm it up. Also, didn't I mention that all the propellants used were liquid? How they managed to make pumps and pipes resistant to cryogenic fluorine and scalding hot lithium? Beats me. Anyways, the liquid lithium would be injected to the now preheated fluorine and react violently. Then the rest of the hydrogen would be let loose and heated up and accelerated by this reaction. Then any traces of hydrogen fluoride would be turned into hydrofluoric acid by the moisture in the air. Now let's talk results. This test engine managed an ISP of over 530, way better than any chemical rocket. But why go through all this trouble just to make a slightly more efficient rocket engine? Well, you'd need an engine like that in order to build an SSTO. An SSTO, or single stage to orbit, is a spacecraft that could get into orbit without using any boosters or dropping any fuel tanks. But these things are very hard to build since chemical rocket engines aren't hardly efficient enough. So if you wanted an SSTO, you would either have to do some clever engineering or make your engines way more efficient. The Delta Clipper was a prototype SSTO built for the United States military by McDonnell Douglas. It had the capability to deploy a small payload into low Earth orbit. This payload would probably be a small spy satellite or other devious spacecraft. These kinds of probes are usually in a polar orbit, so they can scan any part of the planet. Because of this, the Delta Clipper would need large cross-range capabilities by being designed to have a somewhat lifting body, so it could more easily control where it would land. Now it's time to talk about the most exciting part about this ship, its VTOL capabilities. I mean, nowadays, this doesn't seem that impressive, but back in the 90s, no one had ever heard of such a thing. There was a 1/3 scale prototype built to prove that it was possible, and it worked. There were many test flights, and the progress for the program was going great. Can we build another one? Another SSTO concept was the X-33 VentureStar. This spacecraft's engine was quite unique considering it was flipped inside out. An SSTO would need engines that work well in a vacuum and in an atmosphere. You see, a sea level engine works fine in the atmosphere, but as altitude increases and the plume spreads out, that leads to wasted thrust and a lower ISP. You could easily fix this by expanding the nozzle so it works better in a vacuum. But then at sea level, you'd have the opposite problem. Conventional rockets get around this by using different stages with differently optimized engines. But the Aerospike solves this by flipping the nozzle inside out. In atmosphere, the pressure would make the plume hug the inside of the spike, but in space, the plume would go straight out. This project got very far in development, even having a test engine built. But this whole thing would have been too heavy. They tried to replace the heavy structural parts with lightweight materials, but those would be a lot more expensive. Another SSTO concept was the Star Raker. What made it special was that it would take off horizontally. You see, it didn't just have rockets, it also had multi-cycle jet engines. During initial ascent, the engine would be in turbojet mode. This would have the intakes wide open and the nozzle plug fully retracted. But once it got to a certain speed, the intakes would constrict, the turbines would be bypassed, and the nozzle plug would fully extend. This switches the engine into ramjet mode. This mode would get the Star Raker all the way up to Mach 6 before the jets lost power and the rocket engine would take over. Unlike the Shuttle, it didn't have an opening cargo bay. Instead, the entire cockpit and nose of the spacecraft would tilt back to release the cargo. The Star Raker was also meant to be rapidly reused. It would land on a runway, refuel, and then take back off again. The reason they wanted to make a spacecraft like this is so they could make a giant solar power station in low Earth orbit, with huge solar arrays that would somehow beam the energy back down to Earth and power entire cities. You know what? I hadn't mentioned a single Soviet spacecraft in this whole video, and that's kind of for a good reason. Unlike America, the Russians are very stingy with their spacecraft concepts, and the ones they do release out to the public are just different Soyuz variants. But there is a fully reusable heavy lift space plane we could talk about real quick. This is the Energia Ergon. Of course, it's part of the Energia family, which I briefly mentioned in the part 3 of the History of Rockets series, which you should definitely go check out. Anyways, this rocket was essentially just a modified Energia, with the side boosters moved and added wings and heat shield tiles to the bottom. The entirety of the main spacecraft was designed to reach orbit, where the top section would fold open to reveal a cargo bay. Once its mission was done, it would re-enter the atmosphere and glide down on a runway, just like the Braun. The side boosters closely resembled the ones used on other Energia spacecraft, but with one key difference: deployable wings. After stage separation, these wings would extend, allowing the boosters to glide back on a runway rather than crashing into an ocean. This rocket really never got far into development since it was overshadowed by the rest of the Energia program, and it was eventually cancelled when the Soviet Union stopped existing. Now that we're talking about space planes, let's talk about some shuttle-derived vehicles. The SRB-X is possibly one of the ugliest rockets ever designed. It's a variant of the Ares 1, which had 2 radial SRBs on the primary SRB. This rocket was designed to be very cheap way to haul stuff into orbit. To do this, it would reuse as much shuttle tech as possible, mainly the 3 SRBs. It would even launch on the same pad as the shuttle, since building a new one would be very expensive. This is why the radial SRBs are so freakishly spread apart, is to align with the SRB holes. This thing was only meant to carry cargo, meaning it was never intended to be crew rated. I mean, thank God, even if it had a launch escape system, I have a feeling that no sane crew would want to launch on that thing. Let's take a look at another shuttle-derived vehicle, the Jupiter 3. The whole thought process behind designing this was, let's combine the Shuttle program and the Apollo program. The result of this unholy matrimony was 2 external fuel tanks, each with their pair of SRBs, feeding into 5 RS-68s, upgraded from the Shuttle of course, all clung on to a modified Saturn V. The RS-68s would be jettisoned after the external fuel tank was empty. The second stage resembled the first stage more than it did a second stage. It's like they couldn't figure out how to feed the fuel into the J2Xs, so why not just slap some more engines on there? The comparably normal third stage could be refueled in low Earth orbit to send, and I quote, more payload to Mars than we know what to do with. But how much payload was this really? Well, it was proposed to have a payload capacity of over 1,000 metric tons. That's about 2.205 times 10 to the power of 6 pounds. More than double that of the Sea Dragon. I'd say that's a good place to leave off. If you've made it this far, please like and subscribe. And you'd probably enjoy my other videos too, so you can go check them out. Also, if you have any ideas for the next video, make sure to leave them in the comments below, and make sure to stay tuned for the next video.